Hello, hello. Am I audible? Okay, so let's start with generating function session. Uh, Generating function kinda ruined maths for me because like previously I used to think in terms of combinations, permutations, but I still do. But most of the tasks are pretty much simplified for me using generating functions. Uh, I don't, I don't want to say that like it's very simplified topic, but yeah, like if you practice it, like it's very straightforward. Like you don't need to just solve those equations and you will get your answer kind of stuff. This is the way I look at generating functions, and we will take a look at it with more the more task you solve, more understanding you will get about this generating functions. But yeah, like I have used it so many times, and I guess people people that know generating function know that it's very underrated topic. Okay, let's start. If you guys don't have PDF, you can wait, I have pasted in chat the PDF link. Okay, you can, I have pinned it. Wait a second, let me pin it so you can also see everyone. You can open the PDF also if you want. Okay. uh, so what generating function is basically, we use polynomials, right? How polynomial, basically, polynomial have two parts. One is coefficient part, which is this ai, and xi, x to the power I. So this part we use mostly, and this is the way or count for that part. So if I want to say, uh, I have to choose anything, so how many ways to choose? It's ai ways, but for the ith portion, right? So mm, 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 yeah, you could also call it as a state. This I can be also called as dp state. I can be also called as dp state. So you don't need to write in terms of array, because if you write in array it looks like something like this: I equal to 0 1 2 3 4 ai a0 a1. Instead you write in terms of polynomial, right? So this will also help you in understanding knapsack if you try to learn it in a good way. This will also help you understanding knapsack. Knapsack is very simplified using this, but yeah, we will discuss very basic cases today. Okay, so uh, before that, what we will do is we will understand first the very basic counting principles. I have also taught this counting principle in my previous DP sessions, and these are very important. Like people take it very lightly, but when there are like DP transitions and on multiple states and all, like what's my first advice is to draw the basic graph, like when it is addition, when it is multiplication. So if you are traveling different routes, so it will be plus, right? So if you want to calculate answer for this state, the answer for this state will be derived from both of the equations, because we have two choices here: either this part or this part, a or like a or b, right? So answer, uh, propagation part, or any kind of logic you can say for this, any word you can use for this. uh, so hence, whenever there is we have choices, we will do the addition, but when we don't have the choices, what will happen is we will do multiply, right? So let's say I have my answer here as some x2 calculation which might be derived from here, and then and this x1 is something like this. Or so what we will try to do here is we will try to multiply this x1 into x2, because those are like cross product, or number of ways to get from here to there, something like this. Like this is my state of mind when I think in terms of DP, that I will try to find out nodes, or and then figure out the relationship between those nodes, something like that, because it makes my thinking much more simpler, rather than defined to some state like dpij, then doing the -1 dpi -1. Like usually people are more constrained on like more fixated on this kind of dp, like writing recursive dp, like something like this: recursion of I-1 j-1, and any kind of off by 1 dp. So people are more fixated on this because like they are mostly used to solve like this. So but if you have more flexible mindset, right, in terms of for the state manipulation, or considering state as like more flexible term rather than a very static term, that so you will get much more detail, or you could say you will get more options to think if you are more flexible in terms of state. Okay, so in terms of that, the or rule and rule is helpful, but for generating functions, or rule and rule is very simple, right? So if I want to write that I let's say person a has at person a can spend at most let's say three coins, let's say, or 3 rupees, let's say. Okay, or $3, anything. Okay, or just call it unit. Person A can spend at most 3 units. So what does it mean? At most 3 unit. It means he can spend 0, 1, 2, 3. Right? So what we could do, we could write this state in terms of polynomial. Right? So what we'll do is 1 x raised to the power 0, 1 x raised to the power 1, 1x square plus 1x cube. We don't need to write this one. It just I'm writing it for convenience. And then you can also write 0 plus 0 x raised to the power 4, but it's again 0, so doesn't mean we should do that. So polynomial for a is something like that. And let's say there is another person b who can spend at most 2 units, right? So the polynomial for b will be similar, which is 1 x raised to the power 0, 1 x raised to the power 1, and 1x square. And the moment I say that how much, what are the total number of combinations that I could spend, let's say 4 units. So what could happen is we can just multiply a and b, right? And the moment you multiply a and b, you can easily see that whenever the power combines, it will combine, and what we need exactly is the x raised to the power 4 ka coefficient, right? Because x raised to the power 4 means some money will come from a, and other remaining part will be coming from b, right? So it will be summation r equal to 0 to r equal to 4, coefficient of this a r x raised to the power r into this, let's call it b, and this will be 4 minus r, and x raised to the power 4 minus r. It looks mathematically complex, but in terms of if you think it intuitively, it's just that what power sum up to 4. So this 2 2, this 2 2, or 1 2 2 3 1, and that's it, I guess. There is only two combinations, either like 2 from a and 2 from b, or 3 from a and 1 from b, right? And when you do the coefficient summation, it will be coming the same. But this looks very simple, that why are we doing in terms of equations and all. uh, you can see here, like it's much rather simple to think directly that I can take 2 coins from a and remaining from b. But the thing is, when stuff gets very complex, right, that instead of 3 units I could say I have 10 is to 6 units, and B has 10 is to 6 unit. So I could directly multiply those polynomials using some polynomial multiplication black boxes like FFT and all. But we are not discussing that part. We are just discussing very simple part, that how we can simplify the process, how we can apply the for loop, because all we need is just one coefficient, right? So yeah, that's the part that we will do. So all we need to do is whenever there is and operation that I need A and B, we will do the multiplication. A has multiple choices, so we will do the plus part here because that's the or choice. Either so A can spend either 0 coins, A can spend either 1 coin. Uh, this is the uh, kind of like representation. We can mathematical representation of how A can spend his amount. So this equation just defines that. Okay, and if you look in okay, so there is I will also take PDF example that in PDF or rule they have chosen uh, you add their polynomials, correct? So if you have option of A or B, you just add their polynomials, right? Apple's polynomial x square, banana's polynomial x cube, and you will just add them. It's not necessary that it should be related to only one quantity. This is very good example, by the way, that it shouldn't be related to one quantity. So let's say I wanna buy apple or banana from fruit class and some other quantity from juice class, right? Juice or water class, right? So what we could do is, let's say cost of apple is 2 or banana is 3. If both cost is 2, you can just add, you can still add it, it will be the same combination. And similarly for juice, we have what was the answer here, 1 and 2. So x raised to the power 1 and x raised to the power 2, right? Now this two polynomials can be used as combination of fruit and juice. So apple and juice, apple and water, or banana and juice, or banana and water. It just means that we are adding the cost, but if we do using polynomial multiplication, it becomes not simple, you could say, for small cases, but you can handle it very easily. X squared for if it's a series, if it's a big series, right? Like let's say x raised to the power 0, x raised to the power 1, up to x raised to the power 1000. So this kind of state representation is very useful in terms of polynomial rather than just writing normally. And it keeps like if you have predefined templates uh, or like libraries that you could use, so you can directly store those number and directly multiply them. So in that term it's also useful, but most of the cases you should target to not use FFT and all, and TT basically, right? Never get into this stuff. Always try to think in on very basic stuff, specifically for tasks like A, B, C, D. Mostly, like this will never be used. So this in terms of generating function, if you are using generating function, make it use generating function to simplify your thought process, not complicate the stuff. Okay, so let's start with ordinary generating function. And okay, sorry, I have forgot to multiply this polynomial. So after multiplying this polynomial, if I need to check how what combinations gives me the cost of 4, you can again see x cube x raised to the power 1 gives combination of 4. So after getting, so all you need to do is use this representation. This means I need coefficient of x raised to the power 4, and it just means that 3 plus 1 equal to 4. So 1 plus and 2 plus 2 equal to 4. So again 1 into 1. So total 2 ways cost, total cost of 4. Total cost of 4. Okay. So that's kind of generating function, that all we need is the polynomial. And even if we don't need exactly x raised to the power 4, we need multiple terms. So polynomial multiplication can help us with that. If you need multiple terms, you can use that. So it just means that you will do a for loop. Let's say you don't need to write this FFT entity. All you need to do is write a for loop for r equal to 0 to the term you need, let's say 4. Take one coefficient a raised to the power r from left polynomial x raised to the power r, and obviously you need x raised to the power 4 wala coefficient, x raised to the power 4 coefficient, this one. So all you will do is multiply it with the remaining term, which is 4 minus r. And because you have chosen your storage as an indexed array, how you will store the polynomial, you will store it as an indexed array. So at 0th position you will store the x raised to the power 0 ka coefficient, at 1th position you will store the x raised to the power 1 coefficient, and similarly. So all you will do is this, and if this index is negative, obviously you will return at 0. And b raised to the power 4 minus r, x raised to the power 4 minus r. So the moment you multiply this, it just becomes a r b 4 minus r, x raised to the power 4. So sorry, not this one, but this is the coefficient of x raised to the power 4, ar. And if you think it in a uh, physical significance, it just means that r plus 4 minus r equal to 4. So we try all the combinations that is possible from left and right. All we are trying to understand is how polynomial multiplication relates to our daily life problems, right? Daily life task or something like that. Okay, so let's start with OGF. This is the most common one, or not common one you could say, but like mostly used, you could say. Mostly used. And it looks something like this: OGF AI x raised to the power I and summation I equal to 0. uh, you don't need to get scared about this signs, right? Always try to uh, get used to this. Like, this is very common. This is just a for loop, you could say, if you want to understand this way, that I equal to 0 to limit is just a for loop from I to limit, basically. But what happens is, like, there will also be the case when I will write I equal to 0 to infinity, right? Then in that case, you can't write using for loop. You need to write, because I know that, like, if I write 1 plus x square up to x raised to the power infinity, there is a formula for that. We'll prove it in few minutes, that this is the formula. You might have heard this, might in 10th grade, or when you have learned about this geometric progression, you might heard about that. But it's very simple to derive. We'll just derive it now. So it just write it as s equal to this 1 plus x, and multiply it with this, so it becomes the same series except for x plus x square up to x raised to the power infinity, and just subtract it from both sides. So it becomes, s becomes equal to 1 upon 1 minus x. It's very simple to derive, but full formula, because I will tell you why it is useful. Okay. Uh, mm, 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 mm. This is ordinary generating function. Okay. Huh. So when to choose ordinary generating function? When we don't need permutation, we just need combination. When we only need combinations. Wait a second. Okay. Uh, okay. No other doubt. Huh. Go ahead, bro.
Yeah, Navneet. So basically, uh, I mean, it's getting bit math heavy. So can you explain with any real world example along with the side so it will
Uh,
help us to
it
understand?
is math heavy, na? It is math heavy. The name itself is generating function. Like, see, you will think it as math heavy, but there are some most tasks that are related to generating function are just solving equations and all,
Hmm.
playing with equations. Like, this stuff is new for you, so
Huh.
you might feel it as math heavy, but once even if you solve at least uh, 8 to 9 tasks in the PDF na, so you will get quite used to it. Like, this is not very tough. Like, the pattern is almost similar in everything, but what it does is it simplifies your thought process, it streamlines your thought process, because you don't need to think much. Because like whenever there are like combination task on lead code, your brain freezes mostly, that what combinations is going into what. But in using generating function, it's very easy. Just write the state map like this, ai x to the power I, and just multiply those polynomial where whatever you need basically.
Correct. And the tasks that that you will give basically will basically cross verify that we have understood the generating functions, right?
I have here like this lead code distribute candies. We will discuss this one.
Okay.
Don't worry about that.
Yeah. Cool. Cool. Thanks.
I was trying to cover this definitions in PDF basically. Okay. So
Yeah.
uh, choosing items, yeah. So I will also write this in definitions here. Choosing items, bags of making change partitions is important. Partitions is very important. Like, partitions is basically this x1 plus x2 plus blah 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 equal to n. Like, you might have seen this so many times. You might have seen this in stars and bars. Some of you might have heard this term, stars and bars. And another one is define 10 equations and all. Like, there are various stuff, and using generating functions this will get much simplified. I will explain this also, if if we properly manage the time today. I will explain this to stars and bars. Okay. Now okay, before starting this lead code task, let's learn this formula, which is so basically what we are used to do is, uh, we write the series, infinite series, something like this, x to the power 4 up to x to the power infinity, right? So it just means that we can write this as 1 upon 1 minus x. What's the physical significance of it? It means that I can choose any number, right? For my eighth, like let's say I have three three uh, 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 three people, let's say, or any kind of okay, one person can choose any number. So how would I write in terms of array? I can't write in terms of array, right? Because array is kind of like maximum 10 is to 6 ka space. I can't write in array. So what I do, I write it like this. But I can't even write it like this, because if I write it like this, uh, there are infinite terms. So what we do is we derive this to this, and obviously like we assume mod x is less than 1, although it doesn't matter, because this is just uh, simplification for this series. It's called convergent series, but that's the mathematical part. We don't care about the mathematical part. All we care about is how we can use these equations multiple times or at many places, right? So anyway, so all you need to learn is this part, that 1 plus up to x to the power infinity ka sum is 1 upon 1 minus x. Now let's say I need the combination that if three people, one person can choose any number, and I have three people total. So how many ways to write the sum as 4, let's say? like first person chooses 2, second person chooses 1, third person chooses 1, right? So if you try to write it using for loop, it will get very cumbersome, right? So we won't do that. What we will do is we will write 1 upon 1 minus x, because it's the and choice, so we will multiply it by 3 times. Although I will multiply this polynomial 3 times, but instead I will just write it equivalent as 3 times. Now what will happen is it becomes 1 upon 1 minus x raised to the power minus 3. Now this is the formula you need to learn. Basically you can how to learn about this. There is, the formula is very simple: 1 upon 1 minus x, or uh, I will write it in separate page. 1, okay, I will write it orange only. 1 minus x raised to the power minus n is just uh, n plus r minus 1 c r minus 1, something like this. Wait, what am I missing here? Acha, okay, my bad, 1 second. So this one is correct, right? X raised to the power k. Okay. Acha, now I remember. So how you could remember this? There are two ways to remember this. Like how I used to remember is I remember using this way, that I remember that x1 x to the power k is equal to n. Then the solution is basically n plus k minus 1, something like that, right? Stars and bar, n items from k distinct types, n plus k minus 1. Okay, anyway, we will just write the short formula, not better to remember rather than getting into calculations. So x raised to the power n of coefficient 1 raised to the power x or raised to the power k is just n plus k minus 1 c k minus 1. That's it. Just remember this formula. So if you want to calculate the coefficient of x raised to the power n, if you multiply the equation k times, the formula is this. Because this can be derived very easily using factorials, right? These are basically n plus k minus 1 factorial upon k minus 1 factorial upon n factorial, right? So this is the formula. You need to remember this. See, I am again saying you that this will look very math heavy, but if you try to solve at least 7 problems, this will get very simpler. Like this, because this is just a formula usage. Like there is no creativity applied here, nothing. The formula can be applied at so many places and for so many tasks. So you just need to grind through like 5 to 6, 7 to 8 tasks maybe, and then you will get very comfortable with all this stuff. So this is the formula: x raised to the power n 1 minus x raised to the power k, or you can also write it like this: x raised to the power n 1 minus x raised to the power minus k. Also you can write like this. So in this case, if I need the third term and I need the formula for how many terms give the formula is 4, so it becomes 4 plus 3, uh, because I need the x raised to the power n coefficient for 3 terms. 4 plus 3 minus I'm doing it correct, right? Okay. 4 plus 3 minus 1, 3 minus 1. This is also stars and bars kind of thing, that x1 plus x2 plus x3 is equal to 4. How many total solutions? So you calculate using stars and bars. So it's 4 plus 3 minus 1, c3 minus 1. So either you can remember using stars and bar, like this formula can be remembered using stars and bars formula, because both are equivalent of each other for infinite series. But I have just remembered it like both ways. Like if I forget get confused, I just remember stars and bar formula. So both of my knowledge are like supporting each other, stars and bars, and this normal negative exponent. Okay, anyway, so all we are interested in this formula. Now we don't care, like we know we have this black box, we have this formula, we don't care now how this works and all. We just have this formula. Now we will use it. How we will use it, we will see in this lead code task. So the lead code task is total number of ways to distribute n candies among three children, right? Such that no child gets more than limit candies, right? So how we could write in this in terms of generating function, right? So what we will try to do is, let's consider only one child. For one child, what are the possible numbers of candies is x raised to the power 0, x raised to the power 1, x raised to the power 2, up to x raised to the power limit, because this is the state of dp, right? Coefficient is 1 here. So this is the state for one of the dp. Now what will happen is we can write, uh, now this is for one person, one child. We need this for three child, because we need it for three child, that's a and condition. So we will multiply these three polynomials. So if we first we will try to write this as a formula, uh, which is just x raised to the power limit plus 1 minus 1 upon x minus 1, or better to write it this way, I prefer to write it this way, limit plus 1 upon 1 minus x, right? Now the moment I did this, I got my polynomial for one child as like this, right? Now what I will try to do, I will multiply it three times. So my answer becomes 1 minus x raised to the power limit plus 1 ka cube into 1 minus x raised to the power minus 3. Now here the formula is helpful for us. Like we know any power for x raised to the power n in 1 minus x raised to the power minus k is just n plus k minus 1 c k minus 1. This is the formula. Now we will just try to find our answer. There is another method here which is inclusion exclusion. We can use it, but we will just try to expand this formula, which is just 1 minus, I will just put limit plus 1 equal to p equal to limit plus 1 1 minus x to the power p cube, which is 1 minus 3x. If you guys remember the formula, it's just 1 minus 3x plus 3x square minus 3x cube. This is the formula. So we'll do the same thing here. Instead of 3x, it's x to the power p, and it's 2p, and here it's 3p, right? Oh, sorry, it's 1. X to the power 3p. Now, the moment you see this, there are only 4 terms that we are interested in. And if you see the lead code question, there is also answer in terms of 4 terms. The answer is based on inclusion exclusion, but in polynomials it's very simple now. You don't need to think much. There are like only 4 terms, 1 minus 3 plus 3, and we are basically interested in this power. All we need is how many ways to get the candies. The question was such that no total number of ways to distribute n candidates. So all we need is coefficient of x raised to the power n in this multiplication, basically this total multiplication, right? Now this formula we know, n plus k minus 1 c k minus 1. Now if you guys don't want to solve this, just give just write this derivation. If you are confused about the math part and you want to solve this in contest, what you could do is uh, just write in Gemini or chat gpt, anywhere, or Wolfram Alpha. Try to write this and it will give you the exact answer, which you can directly copy paste. And you can also use Gemini and just ask Gemini that write generating function for this. See, this is the thing I was talking about, that even if you don't want to work with maths, you can have a partial idea and use that idea to speed up your process. So you don't need to brainstorm that how inclusion exclusion, how you will draw the Venn diagram, what state you will choose. Just put up the states, multiply them, that's it. Gemini will handle all the equation manipulation stuff, right? You don't even need to think what coefficient will get getting added to what. Gemini will just give you the Python code for you, right? So you can just ask to Gemini or any AI that write generating function solution for this. You just need to recognize what equations or what questions can be solved using generating function, right? So we are just trying to understand that part. Once you get that, just ask Gemini and it will write the generating function for you. So that part you don't need to even waste time. Okay, so let's take one more example. Like here the p is limit plus 1. Now it will automatically handle all the equations part, that it will get the coefficient, that x raised to the power r ka coefficient is this, which is k is here 3, right? So k is 3, which is and x raised to the power r ka coefficient is this, so r plus 2 c2, right? And it will multiply this with this. All we need is x raised to the power n ka coefficient, so n equal to any power here. Like let's say I consider x raised to the power p. So here in this I need the total power as this is basically x raised to the power r ka coefficient. So I need here n minus p ka coefficient in second polynomial. So it will give r minus p. Sorry, in place of r you just need to put this n minus p basically, and you will get the n minus p wala answer. Like there are various the equation is big, you can just use Gemini to calculate this for you. But see, this is the most good coders think like this, that they don't figure out exact details uh, in their brain. They kind of like get the very rough idea and then just expand on that. This is called kind of like, I called it a DFS strategy, that you have a rough level idea and then you expand those nodes later on, whatever you need. So you don't need to think exactly what equations will getting manipulated. You just need to think about this, that there are four terms in this, and obviously this is the series, so this four is getting constrained to only four terms. This is the thinking part. And once you write it down yourself, you will get much better understanding, because obviously I am uh, used to this stuff, so I can say this, but you will get little bit practice. You will need little bit practice for this. Okay, so this is the one thing. And similarly, like you can also say for stars and bars, it's the same thing, that x1 plus x2 plus x3 up to x raised to the power k is equal to n. Let's say so you need to find the solution. Now you need exact, you know, the exact let me try to put the heading here, stars and bars. This is very common, stars and bars. uh, you need total number of solutions for this, such that, and we obviously know that x1 greater than equal to 0, x2 greater than equal to 0, x3 greater than equal to 0, and n. But you know stars and bars solution for this, which is n plus k minus 1 c k minus 1, right? Everyone, I guess everyone remembers this formula, and if you don't, you should remember this. This is very useful formula. And but here the x1 is greater than equal to 0, so the equation for x1 becomes, or all the variables basically, it just becomes this xi is by the way this different and that is different, 1 plus x square up to infinity, because all the possible numbers are there. X1 can be 0, x1 can be 1, x1 can be 2, x1 can be 3, x1 can be infinity. So this is the state for xi, right? So what I will try to do is, because I need all the solutions together, right? So I will multiply this exact same equation up to k times. So all I will get is 1 upon 1 minus x raised to the power k. And you can remember this formula. This you can always remember. But now I can, for stars and bars, what happens usually is you remember the formula and you will get directly the answer. But the moment they change little bit, like at least for me, I get confused usually. Like, or maybe I am biased toward generating function, but yeah. So what happens is, let's say instead of 0, I put it as 1, x1 greater than equal to 1, x2 greater than equal to 1, x3 greater than equal to 1, or some variables x4 greater than equal to 5, let's say, anything. So what happens is, in this case you will get very confused. Like, if you think in terms of stars and bars, you will get very confused here. So what you could do is, obviously you can manipulate the equation that x1 minus 1 greater than equal to 0, x2 minus 1 greater than equal to 0, and put t as new variable, t x1 minus 1. So x1 becomes ti plus 1 basically, and this plus 1 goes to right side, and n minus 1. So all the summation part, uh, a ai basically becomes this one, that t1 plus t2 plus t3, plus up to tn, oh sorry, tk, becomes n minus summation this variables, 1 plus 1 plus 1 minus 5, or something like this. You can solve this thing, but this is a limited set, limited application of this, that x1 greater than equal to 1. Uh, Obviously I could set limit that x5 is less than equal to 6, or x5 can only take 3 elements, which is 1, 2, or 3. Then what you will do, then you cannot just manipulate this way, right? Here, this is the place where generating function shines. uh, Whatever the state is, you can just directly write that state. So basically x1 greater than equal to 1 means, just write x plus x square up to infinity, x to the power infinity. So it just means x into 1 upon minus x. x2 will be the same. So whatever the starting coefficient is, you will just multiply it by that, and remaining term is same, 1 upon 1 minus x. And you can just multiply. And now the beautiful part about this is, whenever there is a uh, infinite numbers, all you could do is just combine those with 1 minus x, and this 1 minus x always combines together. It will combine and it will look something like this, 1 minus 1 rs. And all you need to do is multiply the numerator coefficients, x square, x cube, whatever the starting part is, but this part is always common. And based on this part, whatever total number of terms you get, total number of terms you get, uh, and obviously the subtraction part, like let's say you need x raised to the power n coefficient, then if I got 5 from here, in this left side you will get n minus 5, all the total parts, right? So in O of n, you will get your answer. This is the beautiful part of generating function. Now if you try to solve this with dp, dynamic programming, the thing will get very complex. But all you could do instead, just write whatever possible solution in terms of power, right? So if my x5 can take only 1, 2, and 3, just write x5 as like this, x plus x square plus x cube, and multiply those polynomials. That's it. I'm taking very complex example, by the way, but things won't be that complex. Things will be much simpler. Just that I'm using different representation, that x5 can be whatever, x3 can be whatever. But usually the stuff is symmetric. So uh, this equation can be just written as like multiplied by k times, something like that. Most of the cases are symmetric. Anyway, uh, if you guys are confused, just remember this formula. Just remember this stars and bars formula, and also remember that our where have I written this thing? This coefficient, that x raised to the power n ka coefficient, and obviously uh, you can remember stars and bars formula, and both at the same time. Both are exactly the same because it's the exact same thing. Because I can write x1 as same 1 upon 1 minus x, and you can remember the formula. I guess I have also written this in PDF. You can also try to read that. Okay. Summary. I haven't touched EGF. Okay. Now let's jump to EGF. Anyone have any question regarding this about OGF? Okay, never mind. Let's start with EGF. By the way, again, I'm warning you that this topic will look tough to you. This is not a tough topic because I'm considering it on very basic level. Because you guys haven't solved much task related to this, so you guys might find it very difficult. Obviously, whenever we learn something new, it's very difficult for us. I might have also found this difficult at the start. So this OGF was related to combinations that I could select two objects, three objects, but it doesn't consider that, let's say, how many permutations are there. So 1, 2, 2, 2, 2, 1, something like this. Now, if you guys might have heard about multinomial theorem. What multinomial theorem is basically, uh, it gives n factorial upon r1 factorial, r2 factorial, r3 factorial, something like this. Total ways to place this object when we have r1 similar, r2 similar, r3 similar, and let's say there are k distinct objects, and total frequency summation is n. So how many ways to rearrange? How many ways to rearrange those objects? Okay. So this is basically multinomial theorem, and by same multinomial theorem, you can see I can use the same exact stuff that we did in OGF. We can use the same thing for EGF. Basically, all we need is the power ka sum, but we also need this wala factor. How many? What's the frequency? So, but the good part was that x raised to the power I ka coefficient matches with this I factorial, right? So this is the good part for EGF, and we are just taking advantage of that. So whenever you multiply, you will get easily. And the other part of EGF is if okay, let's consider a very simple series, which is 1 plus x square by 2 factorial, x cube by 3 factorial, up to x raised to the power infinity upon whatever, right? So this series can be represented as e raised to the power x. So let's say I need only even powers, right? Or odd powers. I could write those in combination of e raised to the power x plus e raised to the power minus x divided by 2 divided by 2. Obviously, you can check that the moment we did minus x and plus it with So this term get cancelled. So this is for even, the plus 1 is for even, and the moment we did minus x minus, right? So it becomes odd powers only, right? You can learn this basically or remember this. Mm, mm, mm. Okay, now let's solve some task which is like practice problem. Then you will understand it better, because I don't think just understanding it this way you will get any rough idea about this. Pencil is shutting down. No. Okay. OGF practice problems. Let's practice few problems, then you will get the perfect idea how we use it. So, first problem is for apple, like there are fruits from which we can buy 0 to 2, any number of apples like between 0 and 2. And for bananas, we have 0 to 1. For orange, we have uh, 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 0 to 1 basically. This is also 0 to 1. Because it is a 0 to 1, what we could do is we can write this as a polynomial, right? Which is x raised to the power 0, x raised to the power 1, x square. For bananas, we can choose x raised to the power 0 plus x raised to the power 1. And for oranges, the same thing, x raised to the power 0 plus x raised to the power 1. Now we need to, what we need exactly, how many ways are there by to n pieces of fruit. So if I need to buy n pieces of fruit, I will just multiply those polynomials together, right? Uh, 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 0 to, okay. So in total, I can buy this and I need to buy total n. So I will do, what I will do is just multiply this together. A into B into O, and whatever coefficient we get is our answer. So in this case, after multiplication, uh, our answer is 2. What n value is needed? I'm referring the PDF, by the way, if you guys were wondering. X is to the power 2. Uh, uh, the coefficient of x raised to the power is your answer for n equal to 2. Acha, oh, we need x raised to the power n. And the coefficient after multiplication gets something like this: 1 plus 3x plus 4x square plus 3x cube plus 1x raised to the power 4. So if you need like try to buy uh, total 2 fruits, we can get 4 combinations, right? If you need to buy total 3 fruits, we can get 3 combinations. For 4, 1, right? And similarly, if you want to do the EGF, you can just divide it by factorial, and you will, and then uh, when you multiply it, you will get the kind of multinomial kind of stuff, and just multiply it by n factorial, you will get your answer. But anyway, for OGF, this is our answer. So if I need to buy one fruit, there are total 3 ways, right? A, B, or O. You can easily construct that. Let's try to do the second thing. Infinite supply coin change. Infinite supply OGF2. You have infinite supply of 1 cent and 2 cent coins. How many ways you can make n cents? Okay, so let's consider the polynomial 1 cent. We have infinite, right? So we can generate is 1 plus x square up to x raised to the power infinity, obviously, because I can take 2 cent, 3 cent, 4 cent, any combination. For 2 cent, I can generate similarly 1 plus x square plus x raised to the power 4 up to x raised to the power infinity, right? and the moment we multiply this, it becomes something. This will become 1 upon 1 minus x. This becomes 1 upon 1 minus x square. Right, again you can do the same stuff as equal to this, but just remember this, that the power is getting common between this x square, right? And if you multiply it together, 1 upon 1 minus x upon 1 minus x square, right? uh, you can also write this coefficient here, which is mm, 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 x raised to the power r plus, because it's minus 1, so it just becomes 1 cr rcr. So again, so the coefficient is basically just 1 here, because it's rcr is 1, and obviously you can see the coefficient is 1. And similarly you can get the stuff here. This is also minus 1, but this is x square, so it becomes x raised to the power 2r, which is again the 1. So whatever combinations are there, you will get uh, after multiplication. Like let's say I need x raised to the power n, so if I chose r, this will become n minus r basically, but it should be even, then only it will work. These two polynomials are separate. This is a polynomial, this is b polynomial. Okay, so this is something like this. Example 2. uh I guess there is also lead code task I forgot, which is based on rolling dice. Like I don't remember exactly, but I am 100% sure I have used this rolling dice on lead code. Maybe I will find it later, but yeah. So you want to find how many ways to get sum of two dice basically, right? So if you want to represent this state of one die, you can write this like this: x to the power 1 x square. Oh sorry, not x to the power 0, up to x to the power 6. Now similarly die 2 will be similar. Now you need to find uh, how many ways to get sum n, right? So it just this x raised to the power 1 up to x raised to the power 6 ka square, and whatever the coefficient is there in x raised to the power n, that's your answer. This is rolling dice. Now let's consider some more EGF examples. I guess, see, in rolling dice, this was more specifically to x raised to the power 6, but the moment I did skewed transformation, like let's say, not skewed, sorry, I got in probability. I Let's say I increase the combinations to x to 7. That numbers, that die is n sided, so it becomes x to the power n. So in that case, you can easily solve this using generating function, because generating function will try to reduce the equation. Will try to reduce the equation, and even you don't even need to think about that. Like you just need to give it to Gemini or Wolfram Alpha, and it will solve for you. But if you try to do like most of the people, first thought is to use dynamic programming whenever they see that rolling dice is there, and they need to roll k dices and all, and they try to do is knapsack kind of thing. That let's say we have total sum as 0 to m, let's say, and then they try to do is get this state, and then they roll the dice that initial state is 0, then 1 2 3 4 5 6, or like up to k, right? So they will try to add 1 1 1 1 1 on this, then again they will generate the recursive solution from this, that 1 1 1 plus state, like the recursion tree. But this will get very complex in that case. but using generating function you can easily solve this. How? Basically, when there are like n state, all you can write is something like this: x 1 plus x up to x raised to the power n minus 1 and n minus 1. And how many dice are there? Let's say k dices are there total. So my solution will look something like this, and what coefficient I need, x raised to the power r, is my answer, right? So, and uh, you can also subtract this, by the way, like when there is x raised to the power k here in power, you can just write r minus k here, and you can remove this x, and this then becomes just x raised to the power n minus 1 upon x minus 1 raised to the power k, right? Now you will, in total o of k, you will find the coefficient that you need basically for rolling die. So the solution from o of m gets to o of k using just maths. Again, repeating the same stuff. You don't need to do the calculation part. You just need to think what state you could write in terms of polynomial, give it to Gemini, Wolfram Alpha, and it will solve for you. Okay, let's take more example on EGF practice problems. How many three letter words you can make using the letters ABC, where you can use each letter at most once? At most once, it means I can use ABC. And how many three letter words? Oh, okay. Why three? I don't know. Because three, it just means that I need this as one, this as one, this as one. Okay. Anyway, so if I could take at most one from each character, but here it can't be empty, right? Because we need three characters total. So it just means that at most one is just equal to one in this case. Hence, and this is a bad example. So anyway, so ABC, we will try to write the state, because here total number of words is there. So ABC is different from BCA, right? This was not the case with OGF. OGF, we need is total number of combinations, right? This is total number of permutations, right? So whenever there is a case of permutation, we will use EGF. So here we need so word problem, password problems, right? Every kind of similar stuff, you can use exponential generating function. Now a can be written as simply as 1 plus x upon 1 factorial, right? Similarly, b can be written as 1 upon x raised to the power same. And you do this like 3 times, 1 plus x raised to the power cube, and all you need is total 3. So x cube ka coefficient in this multiplied by 3 factorial, right? So you can see because I need x cube coefficient and there is the 1, so there are like total of 6 combinations. I just did this math very fast because I know that coefficient of x cube is 1 and multiplied by 3 factorial is just 6. So you can just do this, and if you want to try to calculate it, you can easily calculate it as a b c a c a symmetric stuff. Now b c a b a c, now c a b c b a, total 6 permutations of this for for 3 letter words. And similarly, word with repeated letters, you can choose this is very kind example and very beginner friendly. that how many different arrangements of EEL, right? So we have like two choices of E. So what we'll try to do is how many three letters arrangement can be made from EEL. Mm-hmm. You can use 01, 02, 02. I don't know why they are choosing three and giving us three letter words, because for if it is three letter word, it just means that it's just a combination of that. So answer we can calculate directly, which is 3 factorial upon 2 factorial upon 1 factorial, which is just three combinations, which is E L E E E L L E E basically. But anyway, we are trying to learn here generating function, so we will try to write in generating function. So basically, for E we have two choices, three choices: 1 plus x square by 2 factorial, right? And similarly, another there is only one E, and then for L we have only one choice: 1 plus x. Now when we do multiply, we need to multiply it with 3 factorial, right? So we need x cube coefficient. X cube coefficient can be derived from x into x square, and there is no 3 in this side, so this one is useless. So all we need is basically 3 factorial upon 2 factorial, which is 3 again. X cube coefficient is multiplied by 3 factorial. This is the polynomial, and multiply this polynomial with 3 factorial. Always, like whatever the factorial you need, you multiply it with that. uh I guess whatever the quiz part is there, you can solve it on your own, so you will get what I mean exactly. Try to solve this. And there is also AtCoder FPS series. I will put the link, 1 second. AtCoder, this one, FPS 24 task. uh, uh, Wait, I will share this tab itself, maybe. I need to create this one. Wait, I will create this one because else this will not come in recording. Share this FPS 24. Share. This is the 24 task series. You don't need to solve everything, like these are very tough tasks. You can solve up to C maybe, or E, anything. Like even A and B is good for you for practice. Like you, I have solved up to I, and I know that like it gets very very tough. So I would suggest solve up to C for your practice, and also the quiz examples, and also the lead code portion. This one, count ways. Where is this? Similar question. This one. Share this tab instead. You can see this, right? Like distribute candies among children. This is the one you need to solve. And quiz, and this snack, maybe task sequence you can solve. You can also solve this one. Up to C you can definitely solve. Up to E, let's see what C is. You can solve E up to E, I guess. E is also not very tough. By the way, generating function is called formal power series, right? uh, but we I use generating function name because I learned that way. The name I learned that way. Uh, in Japan, they call it as like formal power series because mathematically it's exactly this formal power series. And another fact that the coefficient doesn't need necessary that it should be integer. You can also solve probability calculation using formal power series. But yeah, it's very useful thing. See, now that you heard about EGF, uh, now that you heard about EGF, you don't need to think about what exactly the multinomial part was there and all. You just need to write the state, multiply it, and you will get your answer. That's why I love generating function. You don't need to think much. You just need to write those polynomials, multiply it, and get your answer. That's it. Any questions?
Navneet, will we get the recordings of this session?
This will be uploaded on YouTube.
Okay, okay, great. So, any plan to conduct any future sessions also like that, or
There will be CSES. I will conduct CSES DP section. I will also show that like how we can use. Yeah, I will conduct DP sessions like CSES DP sections because
okay,
like
okay, great.
wait, like let me stop the recording. Like any query related to this formal power series? Yeah, by the way, this is more practice topic. Like even though like even I am solving math equation in front of you, you need to solve it yourself. Then only you will get the exact gist of it. Like what exactly we are doing here. But whatever the point I have mentioned, like the remembering of the 1 minus x raised to the power minus n coefficient and all, remember that stars and bars se relation wala cheez. And uh, yeah, that's only important, I guess. Most of the stuff I have solved is that only. Anyway, I will stop the recording. Yeah, uh, stop recording.